Welcome back to our next lesson in Chapter 5 of Physics 20. This one's going to deal with orbital period. So we've seen from before that if we have an object spinning around in a circle, that even if it's going at a constant speed, this is considered acceleration because its velocity is changing, and to have that acceleration we need a centripetal force to cause that centripetal acceleration. We've used the formula Fc is equal to mv squared over r for that centripetal force. And to find that velocity, we have also looked at v is equal to 2 pi r over t, and that t is the period or the amount of time that it's going to take to make one circle or one lap. And that's the part we're going to be focusing on today, and we're going to be looking at that orbital period when we're in space. Okay, so that's what we're going to be calculating, but you might be wondering, well, why do we want to know that information? So let's think of some cases where it's going to come in useful. Say we're looking up at the night sky and we see a planet and it's got a moon that is going to be orbiting it. And astronomers want to study this planet, but they're only looking at it in this position. And maybe based off its rotation, it might be exposing the other side of it when it's over here, kind of like our moon, that the same side is always facing our planet. So when it rotates, we would get a better view of it over here to see the whole moon. So we want to figure out how long it's going to take for that moon to go from there all the way to over there, and when we should be using our telescopes again to look at that position. So that would make orbital period useful. Let's say we're looking at another planet like this, and we're looking at it for a long time, and we notice there's some differences in our observations. Let's say we take a graph and we're measuring its brightness. All right, so the sun bounces off of it, and we're measuring the amount of light or brightness that's coming off of the planet and how that's going to be changing over time. And we notice that it doesn't stay consistent the whole time. It kind of looks like this: goes along, then it dips, goes along, then it dips, and then goes along and dips again. So we might want to be interested in what's causing that. And one thing that it could be is it could have a moon that is going around it like this, and whenever it passes in front, that's going to cause those dips that are going down, and so we aren't able to have the same amount of light coming towards us because it's getting blocked by that moon right there. So to look at that moon, again, these are really small and really far away. We would want to know where to look for it in this over here position. So how to know where to look for it is we want to figure out the radius it is from the planet. So we'd be able to use the period information to figure out the radius. So that could be another thing that could be kind of useful. And lastly, let's say we find a new star and we want to figure out the mass of it. Have you ever kind of wondered on the data sheet how they have all these masses of all these planets and of all these stars and how they figure those out? Well, they can't just take a scale in space and put it up to the star and see how much it weighs. It doesn't work really like that. So that leaves us confused with how could we figure out the mass of that star? Well, one way we could do it is we could measure how another object acts around it, how long it takes to orbit, and the orbital radius around it. And this is going to relate to some equations that we had from Kepler and Newton from before. So remember we saw this equation that relates the period to the radius cubed, and he kept getting this number, Kepler's constant, and it was just based off his measurements of the period and the radius, right? And then Newton did work with starting with Fc is equal to Fg, and then with some rearrangements involving v is equal to 2 pi r over t, was able to get the equation of this, which I introduced in the other lesson where we were looking at Kepler's laws. Now I did misspeak a little bit. Kepler didn't actually find this part. This was cut from Newton's calculations, but it kept matching the number that Kepler got for his measurements of the ratio of period squared compared to the radius. And what we end up getting is this formula that I drew here for Newton's, and it gives us a relationship between the period squared and the radius cubed, which gives us this thing that I've circled over here. Now what's important about this is 4 is a constant, right? 4 is not going to change. Pi is a constant, it's not going to change. G is a constant, that's not going to change. The only thing that we would change would be the mass source. So this gives a relationship between the mass of the source of gravity, in this case over here would be the star or the sun, and it gives a relationship to the period and the orbital radius. So if you figure out these two, you can figure out the mass. All right? Or if you know any of these two, you can figure out the third one. So that's the formula that we're going to be focusing on today. It's on your formula sheet, and I know it's a really big equation. I call it the big scary equation, but what it looks like on our formula sheet is it looks like this. It's t squared is equal to 4 pi squared over gms times r cubed. All right, so it's a big equation. We only want to use it when we have to, but it is going to be useful for those things that I just discussed. So let's apply that to an example. Let's say a new star is found with a planet orbiting at 3.0 times 10 to the 11 meters of an orbital radius with an orbital period of 200 days. What is the mass of the star? Okay, I'm going to go back to this equation for a second. There's some important things we need to note about this. Because this G is based off kilograms, meters, and seconds, that's what our other units have to be in. So this time, which we used to often put in years for Kepler's equation, has to be in seconds, which is going to be a little bit annoying to convert into seconds, but that's what it needs to be. Mass needs to be in kilograms, it normally is, and radius needs to be in meters. This is probably the most annoying one to convert, but we need to make sure we have those units. Now, I'd also want you to consider, don't use that big scary equation unless you have to. So don't jump to that one unless you need to use it. So let's see if we can use our other ones. Well, we try and use this one, t squared over r cubed is equal to t squared over r cubed. But unfortunately, that requires two things that have to compare to each other going around the same thing. And we only have one planet here going around a star. We don't have two planets going around to compare. And we don't also see mass in this equation. So that one's not going to work. So this one we only use when we have two things to compare. The next one we had was v is equal to square root of gms over r. Now that does have ms, which is good. That's what we're trying to solve for. But it doesn't give us any information in the question about velocity. So unfortunately, we can't use that one there. So once you've exhausted those two, you don't have two things to compare to, and they haven't told you anything about velocity, then we have to use this big equation. So let's plug into that. But before we plug in, we have to rearrange it. We're looking for the mass of the star, so that's the mass source. Now, it may look like this is kind of difficult to rearrange, but we're trying to get for this ms over here. And what we notice is off the start, it's in the denominator, so we need to bring it to the numerator first. So how we did that was we times it on both sides and cancel it. So times by ms cancels, and ms comes over here. Now at this point, we want to move everything away from ms in the numerator, so I'm going to get rid of the t squared by dividing by t squared. T squared is going to go down there, and we're already done. We have ms, or m source, is equal to 4 pi squared over g period squared times r cubed. So rearrangement not too hard once we get the correct step first of moving the mass source. Okay, now it's plugging in and solving, which it is a lot to plug in, but let's put it in and calculate it together. So first, 4 pi squared, that's just a number. We'll just put that in our calculator. 4 pi squared. Remember not to use 3.14, but actually use the pi button. And now we're going to divide by some big numbers. G, same as always, 6.67 times 10 to the negative 11. And now our time. Okay, now it's really common for people to just put 200 in. But remember, this has to be in seconds. So I'm going to take 200 days, and let's start converting that into seconds. Let's go to hours first. Well, in 200 days, we're going to multiply that by 24 to get how many hours there are. So that will give me the amount of hours. Then I want to get the number of minutes. So I'm going to have to times by 60 minutes in 1 hour. Okay, so I now have how many minutes there are. Then I need to times by 60 because that's how many seconds are in a minute. So 200 times 24 hours times 60 minutes times 60 seconds. That number also squared. So we square that number. And then lastly, times by the radius, times by this number here, 3.0 times 10 to the 11 meters, and that number is cubed. All right, so what I would probably do first is I would enter this in my calculator, get the answer, divide by 6.67 times 10 to the negative 11, get an answer, divide by, in brackets, this number squared. So divide by 200 times 24 times 60 times 60 squared, but brackets around that for squared, and then times that by 3.0 times 10 to the 11 cubed. I'm going to take you through that in the calculator here. So let's start with 4 times pi, use the pi symbol, squared. I'm getting 39.478. Then I'm going to divide by the 6.67 times 10 to the negative 11, get my answer. Then I'm going to divide by that time, so I'm going to put in brackets 200 days times 24 hours times 60 minutes times 60 seconds. Close the bracket and square that number, which is in the bottom. Enter. It's a really small number so far. Now we're going to times by, in brackets, the radius cubed, which was 3.0 times 10 to the 11, and that is to the 3. And I'm getting a number of 5.35 times 10 to the 31. So we'll write ms is equal to 5.35 times 10 to the 31, and that will be in kilograms. So this seems like a reasonable answer, and we figured out the mass of the planet, the star, based off of that information from the planet, which does have some use. All right, there'll be some practice questions asking some of those other situations in the sheet attached, so give those a try, and we'll see you in the next lesson.